Today, we will discuss about nanochemistry. Nanochemistry is the study of chemistry at the nano scale. But how small is a nanometer? A nanometer is 1,000 millionth of a meter. Let's try to visualize it. A pencil tip is 1 millimeter in diameter. That is still a million times bigger than a nanometer. Nanochemistry, and more in general nanotechnology, employs nanomaterials, that are materials that are between 1 and 100 nanometers in size. If we consider that the diameter of an atom is in the range of a few Armstrongs, or tenth of a nanometer, we see how nanomaterials are formed by only a few hundred atoms. Nanomaterials can be made of metallic, ceramic, or polymeric material. They have many applications in medicine, like in drug delivery and diagnosis, and in energy, like in solar cells and fuel cells. Let's use a metallic nanoparticle as a general example. Nanoparticles are particles made by few hundred of atoms that are, of course, nanometered in size. The extremely small size of nanoparticles will cause a change of properties of a material. Let's see the example of gold. Bulk gold is a yellow, shiny metal that is inert, meaning that it is chemically not very reactive. A nanoparticle of gold of a diameter of 20 nanometers, instead, is red in color and is a very active catalyst. When we go from the macro to the nano world, we observed drastic changes in optical properties, so color, chemical properties, so in the reactivity of a material, physical properties, such as melting point, and changes in electrical conductivity. This change of properties is directly linked to two factors: the large surface area versus volume of nanomaterials and quantum effects. Quantum effects are an advanced concept, and we will not unfortunately cover them in this lecture. It is important, though, to understand that the surface area is the chemically reactive part of a material, because the atoms on the surface are the ones exposed, and also because they have more energy since they miss the stabilizing force of surrounding atoms. A nanomaterial can be called so even if it's nanometer sized only in one direction. This is called a 2D nanomaterial, since two of the dimensions are not nano-sized. An example is a very thin layer or a film. A 1D nanomaterial, instead, has two dimensions in the nanosize, like a nanorod or a nanopillar. Finally, 0D nanomaterials are nanometer-sized in all directions, like nanoparticles. Nanoparticles can differ in composition. Metal nanoparticles, for example, can be made of only one metal or multiple ones. In this case, they can form alloys, where metal atoms are mixed together, or core shell structures, where the core, made of one metal, is coated with another metal. Researchers were able to create nanoparticles with many shapes, such as spheres, stars, cubes, rods, and plates. To make these nanoparticles, we have two approaches: bottom-up and top-down. In bottom-up, nanoparticles are produced starting from single atoms as building blocks, making first cluster, aggregations of few atoms, and then nanoparticles. In the top-down approach, instead, we start from bulk material that is then cut down to powder and further, we can say, destroyed to nanoparticles. But there are not only metal nanoparticles. Carbon can form many interesting nanostructures. Carbon atoms, arranged in an hexagonal planar array, form graphene. Multiple layers of graphene form the mineral graphite that is found in pencils, for example. Graphene is a 2D nanomaterial and is the strongest material ever tested. A 1 square meter hammock made with a single atomic layer of graphene can hold up a 4-kilogram cat. We can think of graphene like a piece of paper. If a graphene layer is curved, it can close on itself, forming a tube. Carbon can also form spherical nanostructures that resemble a football, like fullerene. In all of these cases, note that all the carbon atoms are on the surface.